see the show.
What won't be showing on television this year?
Hi, Barbara?
Hi. Are you here to fix my clogged pipes?
I sure am.
Perfect. Come in.
Well, hello again everybody, and as you can see, what I've actually got on the bench here is literally a kit of parts. But the interesting thing is, or possibly interesting or possibly not, what is a kit of parts for? Well, this is actually something called a blue ring tester, and what it is, it's a very basic Q meter. Now, trying to think back maybe 30 years to my school days, I'm trying to think what the definition of Q is. And from memory, it's a ratio between inductive reactance and the resistance of a coil. But I think probably another way to actually sum Q up is it's actually just how well a coil of wire will actually resonate. Now, the Q factor is really useful for looking for faults on things like transformers. Quite often you'll find that if you do a resistance test on a transformer, you can't really tell that much about the condition of it. Obviously you can tell if a transformer's open circuit by doing a resistance test, but you can't necessarily tell whether a transformer winding is short circuit, because the resistance of the windings might be quite low, and of course you don't necessarily know what the resistance of the windings is designed to be. But a Q meter, what that will actually do is it sends a pulse into the transformer, and in theory the transformer will resonate a bit like striking a bell. You hit a bell with a hammer and a bell rings. Well, a transformer is just the same. So this circuit is designed to send a pulse into a transformer, not just a transformer, any thick winding, something with a lot of turns on it. It'll send a pulse into your transformer, and the windings will resonate, they will ring, and this device kind of measures how loud that ring is. So that's what it's designed to do, and these are particularly good for looking for things like shorted turns in transformers. There's really no other piece of equipment that will tell you if you've got a shorted turn in a transformer. Now, the reason I bought this, it was when I was going through the heady days of repairing televisions, or attempting to, and a lot of people were talking about Q meters on the forums because you use them for measuring things like whether or not the line output transformer is good. And you can also use them for testing the yoke on a television. So yeah, that's why I bought it. Now, I'm just checking to see if I've actually got all the parts here, because unfortunately I think it's probably nearly 2 years ago I bought this, and it's been just kicking around in a drawer since, and I'm just hoping I haven't lost anything. I think everything's here. So I suppose I should start off by telling you where I bought this kit. So this kit is from Altronics.com, and I think they do call it the Blue Ring Tester, and that company is actually based in America, and I did actually have to import it, but it wasn't particularly expensive to import this thing. Now, our Blue Ring Q meter does actually come with some instructions, but you've got to download them from the website. They don't actually come with it, so I have actually gone ahead and I've downloaded those, and I can see it on the computer screen next to me, but unfortunately you can't see that. But what I'll try to do is I'm just going to try and put the relevant parts up in the video, so maybe you can have a look at what I'm doing as well. So I suspect today's video is probably going to be, well, is it possible? I was going to say it's going to be less exciting than most of my videos, but yeah, most of my videos aren't very exciting to start with, but yeah, maybe we can just plumb new depths, as it were. So our ring tester does come with a circuit board, and it's quite nicely made, and it is a double-sided board. Just looking at some of the traces on it, it's quite interesting that all the traces are at 90 degrees. You know, there's no sloping and no curves on anything. You've got to be very careful with these traces when you put traces like this that go off at right angles, because the electrons run down the wire, and they can't always turn around this 90-degree bend, and if you're not careful they actually fly off the ends of the trace, and yeah, it makes a mess. You get electrons flowing all over your bench. So yeah, we'll have to see if this works with these square traces. I suspect it probably will. Now, I don't know what you start with when you build a kit, but I normally start with the lowest components, and then I build up from there. So the lowest components I think are probably the resistors, so let's bung them in. So it tells us to start off by installing R15, which it says is a 270 ohm, which I think is that one. My eyes aren't right good these days. I think that's a 270. I can't tell whether that last band is purple or brown. I think it's probably brown. 265 ohms, that's close enough, isn't it, in old money? All good to do now is spot where R15 actually goes. There's R16, so it should be around here somewhere. R16, R17, R15. Oh, that's quite good. I've just noted on the circuit board they've printed the actual number, so there's R15, but they've actually also printed 270 as well. When I do my soldering, I tend to use this 1.2mm stuff for nearly everything, but these pads on this board, they're absolutely tiny, really small little pads. I would have perhaps made them a little bit bigger if I was making this board myself. I think I did mention that I've had this kit really for some time. It's probably a couple of years it's actually been sat on my shelf, and well, I keep procrastinating and putting it off. As I say in a lot of my videos, I'm actually generally quite lazy, and I've also got a very short entertainment span, which means that anything that takes more than about an hour, I'm quite disinclined to actually do it. So we've got 7 2K2 resistors to install next. I think they're actually, I think these are 2K2. If you're wondering why I'm struggling with the reading the numbers on these things, I think unfortunately this LED light I've got, it's either my eyes that are getting old or just the colour rendering isn't great. So although it may look like red, it could equally well be brown to my eyes. So I'm just double checking all these component colour codes. It's not because I can't read resistor colour codes, it's just because, well, because my eyes seem to be failing a bit these days. You might have noticed that I choose to cut the legs at one end of the resistors before I actually solder these resistors in. Don't always do it, but I try to remember to do it, and the reason that I do that is because you find that these resistors that come in a little bandolier like this one, at the ends of the resistors they've got sticky glue on them, and when you actually stick the resistor into the hole, some of that glue will come off and it'll get stuck around the pad. Now if you try to solder that, obviously it just doesn't aid making a good joint. So usually when you take resistors from a bandolier like this, rather than just pulling them off, it is a better idea to snip them off. Well, I think you've watched me putting about enough resistors in, so I'm going to carry on populating this board, and when I finish putting the resistors in, I'll bring you back for some more exciting components. Well, as hopefully you can see, I've gone ahead and I've actually installed all our resistors, and yes, that was a totally non-challenging exercise, but so far so good. So I said I'd bring you back in time for some excitement, and that excitement consists of doing the diodes next, of which there is 3. So taking a look at these diodes, they look like they're something like 1N4148. I think I can just about see the numbers on them, and yeah, they're small signal diodes, aren't they? Well, okay, so I've had 2 goes at bending these legs and managed to get it totally wrong on 2 occasions. Let's see, the third time is a charm. Bah! I'm afraid I'm betraying myself here. You can see actually how long it is since I've actually done any electronic assembly work, and it's like any other muscle, if you don't use it, it tends to waste away. Now over the years I've done an awful lot of electronic board assembly. In fact, I spent quite a period of my life actually working in a production facility where we made printed circuit boards, and there was always a fair amount of hand rework involved because of the specialist nature of what we were doing. So you'd think I'd be better at it, but like many other things, yeah, I just get out of practice. Now, of course, when it comes to building kits, you can build the kit in any way you want, starting with any component you want, and that's part of the fun of doing it, isn't it? Doing it your own way. But a little bit of advice that I will pass on, I'm sure most of you already know this, it makes it much easier. If you start with the lowest components first, the tiniest components, and then work up to the bigger and bigger components, you'll find that the assembly process is easy, because if you actually put some of the bigger components on the board first, they will stop you getting at and make it more difficult to place some of the smaller ones. So start with the small ones first and work upwards from there. So it's capacitator time, so I'm looking for some 1 nanofarads, which I think that's what that one is. And I can't even read it with the aid of a magnifying glass. I need a bigger magnifying glass. In fact, let's get a bigger magnifying glass. I think that's 102, which is 1 nanofarad. But I am going to double check. Yep, 1 nanofarad or 999 picofarads. Close enough for me. I don't know about you, but I do like to use quite a large chisel tip, and maybe that's because I'm quite lazy, but I find that I use the same chisel tip, and it doesn't matter whether I'm working on something that's fine surface mount or on a circuit board like this through hole, or even a big valve radio chassis. I use the same chisel tip for everything, and it seems to work for me. But I do notice that some people seem to be forever swapping tips from one thing to another. I'm just too lazy. So I should have 6 100 nanofarad capacitors, and I think we've got them there, and they're going to be 104. I can actually see that, that does say 104 on them, so that's easy. Oh, they do fit the leg spacing perfectly. So usually when I'm installing capacitors or any other component that's got a number on it, I do like to have all the numbers lined up in one direction, because you get used to reading the board then without having to turn it around constantly. So I always line everything up in one direction. Same with the resistor colour codes. I like to get them all lined up with the tolerance band at one end and the the resistance values at the other. About the only exception to that is regarding the numbers is sometimes if you've got a tall component and you put a capacitor up against it, the number will be obscured on one side. So if that was the case, I would actually turn the capacitor around so I could read the number. Basically what I'm saying is I want to install a capacitor so I can always read the numbers on them. So our little ring tester kit, it just seemed to be coming together really quite quickly. It's a very easy kit to build. It's a very nice kit to build actually. I would actually recommend it. Unfortunately, I do find it difficult sometimes to find just enough hours in the day to, build kits like this. And whenever I do build a kit, I do always enjoy the experience. It's always really good fun. Now I know that most of you, like me, enjoy repairing valve radios, and again I don't like to spend too much time on repairing valve radios because I get a little bit bored at times if the project becomes too big. I kind of lose interest in it. But when it comes to repairing valve radios, the amount of time it takes, as we all know, it's measured in the Lindermass scale, which is actually named after Jim Lindermass. Now obviously 1 Lindermass is quite a long period of time, which really goes from about the Big Bang to the heat death of the universe, with dinosaurs and the first protozoas emerging out of the sea. But obviously because 1 Lindermass represents such a long time, we've actually invented the decibel scale, so you have a dekilindermass. So most of my radio repairs probably take about, I don't know, maybe 10 or 11 dekilindermasses, whereas some projects take even longer. Now, of course, not everybody uses a Lindermass scale. I know that also some people use a Glassinger scale. So, I don't know, I think about 1 Lindermass equals about 6,000 Glassingers, something like that. Put one joint on here. I don't quite like the look of it. It just seems to be a bit bulgy. See if I can just reflow that with a bit of flux on it. Okay, happy with that now. So we're also going to have to install a couple of semiconductors shortly, and 2 come in this little baggie here, put on the piece of anti-static foam. Now it does say in the kit that these don't come with sockets for them, and it says if you don't like soldering directly to a circuit board, of course you can go ahead and install them in sockets. Now I've got to admit, whenever possible, I do like to install ICs in sockets, and it's not because I'm scared of soldering them in, it's just that yeah, it becomes painful to take them out again should an IC fail, and maybe if you was to connect this to something you shouldn't, you could do some damage to it. So I think I would like to be able to pop these ICs out and replace them if necessary. So I'm going to look for a couple of sockets to put in. I'm not sure if we've got any actually. Let's see what we can find. Okay, let's look for something nice. So that's a nice turn pin socket. Has it got enough legs on it? Yep. So we'll have that one. Have we got a number of them? Oh, that one's a bit short. Unfortunately my sockets aren't really sorted into any order. Is that a bigger one? Yep, okay, 2 sockets have been found. Well, it does always really annoy me when I actually install sockets in a circuit board, and sometimes you don't solder them down flat to the board and they're kind of cocked up at one side. So what I normally do to stop that happening, I usually actually put a bit of blue tack at one side to hold the IC socket down. But unfortunately, I can't find any blue tack today, so what I'm going to do is I'm going to try and tack one corner down. And this is where you manage to get your finger on the turn pin and the heat goes straight through and really burns your finger. So prepare to hear me go yelp. Got the IC socket completely flat to the board there, and it's actually the right way around, which is a bonus, isn't it? So here in Yorkshire where I live, we've had the first snow of the year today, and yeah, it's actually quite early in the year here to get snow, in that it's not even December yet, just at the end of November. We've actually had a good 4 inches, which is unusual. So although I was actually planning on going out and about today, it's quite nice to have an excuse to stay inside where it's warm. I mean, it's not just the snow, it's really quite cold and it's very windy outside, so it's not really the snow that's bothering me. I just don't particularly like walking in high winds, and it really is very windy. So it was just a good excuse to come into the workshop and yeah, build this kit. So that was our electrolytic capacitor installed there. Really coming to the end of our build now. Just noticed that there's a switch symbol goes here, so let's put our switch in. Yep, little push button switch. I think I mentioned earlier, this is quite a simple kit, but it's very nicely put together. Every component really is fitted perfectly in the holes and the spacing. So whoever designed the footprints for this board and the switches and things, they've got it spot on. It's not unusual for people to you know, to get them wrong, and it just makes the assembly process a bit tricky. This board has gone together just very, very easily. So putting this switch in, it is one of them components that just has to be pressed into place so it lies flat on the board. So yeah, just doing that. Oh, and the heat's running down the component leg into my finger. That's always a joy, isn't it? So I think the next thing we're going to put in is actually our LEDs, because this doesn't have a display on it as such. It just has a row of LEDs that kind of they indicate the quality factor, the Q factor of the coil. And what you've got to do is you've got to set these LEDs at a certain height, and to enable you to do that, they give you this little piece of plastic here, this jig, and lots of LEDs. So what we're going to do is we're going to put these LEDs in. Now, unfortunately, one thing that they haven't done is that I would have liked to have seen. I would have liked to have seen them indicate the anode and the cathode on the circuit board, and they haven't actually done that. I mean, quite often you might just use like the square pad for a cathode rather than a round pad, just something to distinguish it, or even just put something onto the legend to actually, you know, a little plus or a little K symbol for cathode. But yeah, they've not done that on here. But if you turn the board over, they've actually written into the solder side, they said short lead to this side, so they have described it. Hopefully you can see that on the camera. I'm not sure whether you'll be able to, but it does say here short lead to this side. So they are telling you which way around to put the LEDs. Now, as everybody knows, the short lead on an LED is the cathode lead, and yeah, that's universally true. The only time it isn't true is I once did buy some LEDs from, I think they're about the cheapest you could buy, you know, from China reseller on eBay, and I got this big box of LEDs of all different colours, and all the legs were the wrong way round, so they hadn't followed the convention, whereas yeah, the convention is to make the short lead the cathode lead. So hopefully you can see that this has got a long lead on it, a short lead. It might not come out on the camera. One lead's longer than the other. So the short lead that they're talking about is the cathode lead. So I think my plan of attack will be like some of the other components. What we'll do is we'll solder one leg in first, and then I think we'll just come back and straighten them up and then solder the other leg in. So let's see if we can just straighten these up a bit now. Actually, I think it's about the fiddliest job this, trying to straighten these LEDs up, but yeah, I think they're okay. So let's just thread my test leads here through what's going to be the base of the box. I think these test leads are a little bit too long. I don't want them quite so long. So I'll cut them down a bit. And we're also going to put our crocodile clippies on the end of these. So put the shrouds on first. There's another shroud. Of course, these crocodile clips have those little strain relief barbs on the back, so we're just going to try and fold them over so that they dig into this cable a little bit. And I'm hoping that there's going to be a battery connector inside this case. Oh yeah, got one there, because that is one thing that was missing. I'm sure that most of you watching this are probably quite bored at the level of detail that I've gone into, but some people find it useful to have a reference when they're building these things online. It's easy to copy somebody else's and see how things go together, but this is a particularly easy kit to build, so I don't think anybody would really have any problems building this. It's yeah, it's very nicely thought out. I think what we'll do is, before I put it in its case, I think we might as well just go ahead and I like to deflux these boards. You don't necessarily need to do it with this modern fluxes, they're not very aggressive, the flux that I use, but yeah, I think we will go ahead and just give it a bit of a clean. Just spotted a joint there which I think I could improve on. And I'm also just going to take a moment to do some inspection under the magnifier. Yep, okay, I think I'm happy with that. We probably are tempting fate, aren't we, to screw it down before we've actually tested it, but hopefully this is a relatively simple circuit and it's just going to fire up. Probably not. So finally, we've just got a couple of ICs we need to install now. So what have we got? We've got a CD4069, so that's some kind of an inverter, and we've also got a CD4015, which from memory is a shift register. So we'll go ahead and stick those in. Now I have bothered to get out the strap on, although I've got to admit I don't generally bother to take anti-static precautions outside of a production environment. I think if you're working in a production environment you've got good reasons to do it, but you know, I generally don't take anti-static precautions, and all I can say is that having handled ICs and processors and memory devices over a 20-year period, I'm not aware that I've ever damaged anything through static. I'm not saying it couldn't happen, but I'm just generally bigger things to worry about in life. One thing I wish I did have though is something to actually insert these ICs. Back in the day I used to have some tools which would just squeeze the legs in and present them correctly to the socket here, but yeah, for whatever reason don't have them anymore, and just getting these ICs to line up with these turn pins, it's a little bit fiddly. Usually I end up bending one of the legs over and then swearing a lot. Okay, that one went in okay. And now our 4069, our inverter. So I'm just having to squeeze the legs in kind of one by one to try to get them to line up with these turn pin sockets. They don't have a lot of tolerance on them, these turn pin sockets. The legs either go in or they don't. There's not a lot in between. And of course got to remember to double and triple check that we've actually put the ICs in the right way round, because there's nothing more infuriating than burning chips out because we've put them in the wrong way round. I'm sure we've all done it at some point or another. And there we go, there's our circuit done. And let's treat it to a brand new battery. And does it switch on? Okay, switches on, getting some pulsy lights. Now they do actually give us some equipment to test this with. They gave us a core here, an inductive core, and I think they also gave us some wire. What have I done with that wire? Okay, here it is. Here's some enamelled wire, and what they want us to do is they want us to wind a little inductor and use that to test our circuit with, so let's do that. Well, I think this is going to get a little bit tedious, so I'll tell you what, I'm going to wind this inductor. When I've done that, I will bring you back. So as you can see, I've gone ahead and I've wound our little inductor here on this figure of 8 core, so let's just measure out of interest how inductive it actually is. So I can see that my little Peak Atlas tester here, it's indicating that we've got 1.8 millihenries and 0.024 ohms of resistance. However, the proof of the pudding is what our ring tester says about it. So remember that the ring tester, it's not actually measuring the inductance, it's kind of measuring the quality of the inductor, how resonant it is. And as I say, the mathematical expression would be the ratio of inductive reactance to resistance. So according to the instructions, this particular figure of 8 core with these windings on it is going to produce quite a high Q circuit. So let's try that. So I'm guessing we're going to get all green lights here if it works. Okay, can you see that? So we've got all green lights on there. Now if we had a short circuit on our inductor, I'm guessing that the lights would go off, which they do. I wonder if there's anything we can do to this core to reduce the Q factor. I'm kind of thinking if we put a shorted turn on it, that might help. So should we try that to see if we can get a shorted turn on there? So what I'm going to do is I'm just going to thread another piece of wire on here, assuming we can get it to go in. I'm wondering if one loop of wire is enough to ruin the Q factor of this coil. I don't know, maybe it will be. So I've just gone ahead and I've taken our figure of 8 ferrite and I've just put one turn of wire on it, and I'm just wondering if this one turn of wire, if it's shorted out, will that be enough to affect the resonance of this circuit? Is it going to affect our Q factor? I don't know, let's see if I can just short them out. Yeah, and it does, look. So I'm not even shorting out the actual windings the Q tester's connected to. I'm actually shorting out the secondary. And can you see that? If I just touch these wires together, there you go. This inductor is no longer particularly resonant. We actually ruined the Q factor of it by putting a shorted turn on it. So this is like having the secondary of a transformer with a short on it. So if I just disconnect that wire, you see the Q factor comes back, it goes high. So this is ringing really nicely. And if we should put a short on there, okay, all the lights go out again. So this is working beautifully, isn't it? I'm really impressed with that. This ring tester works really well. Now this Q meter is a very, very basic one. Of course, people like Hewlett-Packard, in fact Marconi, they make some much more advanced Q meters which actually give you a readout of the Q. This just kind of gives you a comparative measurement. It gives you an indication of whether the circuit has got a high Q or a low Q. It doesn't actually give you a value as such. Have I got that on about the right place? Yeah, I think so.
And so what this means is it's like taking a tuning fork and thumping it ever so often, like this.
So the way that a ring tester works is, well, probably one of the best and oldest analogies is, do you remember back in the day they used to employ people to test railway wheels on locomotives? And the way they used to do that is they would actually tap the wheel. Now if the wheel was good on the locomotive, if you tap it with a hammer it would ring like a bell. But if the wheel was defective because it had a crack in it, when you tap it with a hammer, rather than ringing, you'd just get a dull thud. So a ring tester works very much the same way. So inside here we've got an oscillator, and that oscillator is outputting a square wave on these terminals, and that square wave has got quite fast, rapidly rising and falling edges on it. So this square wave, what you do is when we connect it to our inductor here, so this is like our railway wheel. So our ring tester, what it's actually doing, it's tapping the wheel, it's tapping this inductor with this square wave, and then what it's doing, it's counting the number of ring cycles that come back on it. So if this inductor's really good, it's going to ring a lot, it's going to ring like a bell. But if the inductor is bad, I'm going to make it bad now. See, all the LEDs have gone off apart from the bottom one. That's like our cracked railway wheel. I bet we could see how this works better on the oscilloscope, so let's try that. So to carry on with our wheel tapping analogy, we've got the blue ring tester here, and this is connected to the oscilloscope, but it isn't actually connected to the inductor as yet. So what we've actually got is, we've got the blue ring tester. This is the equivalent of the man with a hammer. So he's actually swinging his hammer, he's bashing his hammer up and down like this, but he hasn't got a wheel yet to tap. There's no wheel, he's stood to one side of the train. So what we're going to do is we're going to connect in the inductor now. So I've just gone ahead now, and hopefully you can see I've connected our inductor into circuit, and you can see that the blue ring tester here, it's indicating our high Q. But look at the oscilloscope screen now, you can actually see a perfect example of what we would call a ringing waveform. So here, what's happening here at this point here, the blue ring tester, it's actually tapping the wheel, it's sending a pulse into our inductor, and then what the inductor is doing, it's actually resonating. So again, just like a bell, when you tap it, it rings loudly, and then as time goes on, it actually rings less and less, the bell gets quieter, and you can actually see that in this waveform. So what I'm going to do now is, I've got the secondary winding our transformer, and I'm going to put a shorted turn onto the secondary winding, and you're going to see that that's going to absolutely ruin the resonance of our circuit here. So you can see now that our ringing has completely stopped because our wheel's got a crack in it, because we've produced a shorted turn on the secondary of our inductor here, and you can see that the ring tester, that's just displaying one red light. So again, I'm just going to release this shorted turn, and the inductor's going to start ringing again. So I'm sure you'll agree that our blue ring tester is actually quite an interesting piece of equipment, and it can do something that, well, most other pieces of equipment that we have to hand can't do. I mean, we couldn't actually test a transformer just by measuring the resistance of it. Quite often you'll get a shorted turn on a transformer, and on the primary or the secondary, and the resistance measurement won't really have changed very much. But this ring tester will actually show that up if you've got a failing winding, and it's really about the only instrument that will do that. Now I'm sorry, but I do have to admit quite a serious failure in the review of this blue ring test, because the main purpose of this piece of equipment is to test things like line output transformers in televisions, and also very large wound components like television yokes. But unfortunately, as it happens, I don't have any television yokes or any line output transformers to hand that we can actually do some testing with. But there is lots of other reviews of this blue ring tester online, and most of those reviews do actually show this tester being used to repair televisions. So maybe if you want to see it being used for that particular purpose, you can look those up. Now earlier in the video I did say that our blue ring tester could be used for testing transformers, and in fact that is true. But the reality, it is really designed for testing circuits and inductors which are very IQ. And here we go, you know, the clue is in the label here, blue ring tester for high Q inductive components. Now, some transformers, daft as it sounds, aren't actually designed to be high Q. They're not necessarily designed to be resonant, because that's really what a high Q circuit means. It means that it's going to be quite resonant. But actually for a lot of transformers, they're not actually high Q devices, and you wouldn't want them to be. So for example, here's an audio output transformer which I've removed from some valve radio in the past, Now this transformer, you wouldn't actually want it to be resonant at any particular frequency, because for example if you were trying to play music, you wouldn't want to find that, you know, when you played a particular tone or a particular note of music, the output from this transformer shot up because it was magnifying, it was a high Q resonant circuit. You wouldn't want an audio transformer to be resonant, and in fact they actually take measures to stop it from being resonant. And if you've ever pulled apart an audio output transformer, quite often you'll find a paper shim at the top of the laminations here, and that's actually designed to help prevent the transformer from becoming resonant. Now I'm not sure which is the primary and the secondary, we'll have to try it both ways round. Okay, but certainly we've only got one yellow light on here, so this transformer, yes, it has got some Q, but yellow, marginal, medium or low Q. So this is low Q. Let's try turning it round. And again, it actually does come up with a similar low Q reading. Now I don't know about you, I don't know whether this blue ring tester is telling me that this transformer is good or bad. In fact, the only thing that I can really think to do to try to prove that is perhaps short out the output secondaries and see if that ruins whatever Q this transformer's got. Okay, and yes, we've lost the yellow light and now we've just got the two reds flashing. Now if you were testing this transformer in isolation, and what I mean by that is you don't actually have a spare transformer you can actually try. You can't try this tester on it to actually obtain a Q reading. If you was to look at this blinking yellow lamp here, would you know whether this is a good transformer or not? I'm really not sure that I would be able to make up my mind. Of course, if I had another transformer which I knew was good, I could take a Q reading and then I could you know, transfer the meter onto this transformer, and if it behaves the same, I would have a good idea that it was a good transformer or maybe a bad transformer. But just having the one transformer and just having this indication here that this transformer is marginal Q, well, that reading just takes some interpreting, doesn't it? Probably the nearest thing that I've got to a line output transformer is this little high voltage step up transformer. I think I used one of these in that ESD gun that I built last year, so we can actually just try connecting that up. Let's see what this does. I suspect that this will be relatively high Q, because these are designed, or certainly I found that depending on what frequency you provided these transformers with, it had quite a big effect on the output voltage. So I'm fairly sure that these transformers are designed to have a certain resonant frequency, and because of that they should be reasonably high Q, I would have thought. Well, okay, so much for thought, because again, unfortunately that's only given us the one yellow light. So again, can you tell, is that a good transformer or is it a bad transformer? If I don't have another transformer to substitute, I'm not sure I would be sure. Again, about the only test I can think of doing is to short out the primary to see if that makes the transformer, you know, go worse if the Q lowers. Okay, and I've just shorted out the secondary and you can see all the lights have gone off. So perhaps by doing a couple of tests you can get an idea whether or not this transformer is good or not. So I've also got some inductors here. Now these might look like resistors, but they are actually just little inductors which are designed for going on circuit boards, through hole mounting. And I've got various sizes of inductance. I haven't bothered to read the values, so I don't know which is which, but I suspect the bigger ones are probably a larger inductance because they've got more windings on them. So I would have thought that these probably are designed to be quite high Q devices, so we'll probably get quite a high reading with this one. Okay, and indeed we do. We actually get it going to full scale, so that's a positive indication that this is a good inductor. Okay, let's try one of our other inductors. Well, I don't get any lights with that one, so that's a total fail. I wonder what value of inductance that is. Okay, well it's not a very large inductor that, because our Peak Atlas LCR meter says it's only 30 microhenries. I wonder what the other one was. Okay, so the first inductor that we tested here, that was actually 1 millihenry, so it was significantly larger. So again, there's obviously a limitation to the smallest amount of inductance that this blue ring tester can actually measure. So I've got one final of these little inductors we can try. Let me just see what measurement that is. Okay, that's a bit bigger than the other one, that's 88 microhenries, so we'll 88 microhenries measure on here. Okay, it does measure. We've got it's kind of give us 1 amber light, but yeah, it doesn't measure particularly well, does it? So again, this thing works better on well, I guess you'd expect it to. It works bigger on larger inductances. So let's go back to the first one we tried. Yeah, it really loves that one, doesn't it? So the next thing I've got on the bench, it looks like a little transformer, but it's not actually a transformer. I think this is some form of common mode choke. Not exactly sure, because it's just another part that came out of the junk box. It's obviously some leftover from an old project. So let's just try that. And it does seem to like that. It's giving us some green lights there. I've got another inductor here, and looking at it, I suspect that this might have been from some form of homebrew switch mode power supply. Again, can't quite remember, but I would have thought that this should be reasonably inductive and have a relatively high Q. So let's see if it indicates that. Okay, well, we get 2 amber lights, so yeah, it's medium to low inductance. I expected that to be a bit higher. So the final thing that I've got to test today is this mains power transformer. So this is a 230 volt AC in, and it's got 2 times 12 volt output windings. Now again, I would expect this to have very poor Q factor, because again, you don't want things like mains transformers. I wouldn't have thought you want them to be a high Q circuit. Again, you probably want pretty much the opposite, but let's give it a try. I expect we'll get a very low reading for this. Okay, so we get 1 amber light, so it's kind of indicating a low Q factor component, which is probably correct. And absolutely finally, I have just spotted another component, which is a little taco coil. And again, no idea what this is or where it comes from, but let's try that. This is probably relatively high Q, I would have thought, because that's what they're designed to be. They're designed to be resonant at certain frequencies, so maybe we'll get a good reading for this. Okay, yeah, it likes that. We've got actually 3 green LEDs. That's one of the highest readings we've got. So it likes our little taco coil here. But yeah, I would probably expect that, because these little taco coils, well, that's the whole purpose of them. They're designed to be resonant at certain frequencies, aren't they? And this blue ring tester has proved that. So all in all, how would I sum up our blue ring tester? Well, I definitely think this instrument has got some pros and some cons. On the plus side, the manufacturer's website is very easy to deal with, and they shipped out this product very quickly, and I had no problems with customs or anything like that. The kit is certainly reasonably priced, and the documentation that it comes with is very good. And because the documentation is very good, and it's a relatively simple circuit, it's actually a very easy kit to build, and I would say it's quite suitable for beginners. And I've got absolutely no doubt that this would be the perfect tool for testing things like line output transformers and television yokes. And a more up-to-date use for our blue ring tester would be for testing things like inductors and switch mode power supplies. I think it would probably do that very well. So I think that the blue ring tester really is a perfect tool for testing high Q inductive components. Now unfortunately, although that is a pro, it's probably also the biggest con for the blue ring tester. So it does work very well for high Q inductive components. The problem is it doesn't work so well for components which have got a lower Q, such as mains transformers. And testing of mains transformers is one of the things that I was hoping to do with this. Now it did work to some extent, but I think some of the readings were, I don't know, misleading. If you had another transformer to use for comparison, you could probably do some comparative measurements with it. And I guess that brings us on to another con, in that it doesn't actually give a readout of the Q factor. It actually just gives us an indication using these LEDs. Now I don't hold that too much against the blue ring tester, because if you've actually looked at proper Q meters, they tend to be enormous, great expensive things, quite uncommon and not the sort of thing you're going to find on your test bench. So I'd say that the problem is that the blue ring tester does somewhat lack utility compared to what other pieces of equipment we could spend our precious money on, and that you'd probably find much more use out of you know, a peak atlas, an LCR meter, or a component analyzer, or even a cheap component tester from China. it would just certainly have many more uses on the test bench than the Q tester does. But if you've already bought every other piece of test equipment that's available and you're just itching to spend some more money, I'd actually think that the blue ring tester is a perfectly good place to spend that money. And if you have got things like televisions to repair and maybe switch modes as well, then this would probably be worth buying. But I think for the average user, it's just too specialist. I think it would also be useful if this blue ring tester actually produced an actual measurement value rather than just these LED bar graphs. Now, I think there is some other blue ring testers around. Maybe they've brought out a more modern version that does have a couple of 7-segment displays on it, so it does actually present you with a number, which is a little bit easier to read than just trying to work out how many of these LEDs are lit. However, having said that, I think even the ones that produce a number, it doesn't actually tell you the Q factor, it just produces a value. But I still think that would be an improvement over this. Overall, I am definitely going to give this piece of equipment a thumbs up. It's definitely quite a useful bit of kit if you've got the need for it. Anyway, I think for today, I think we've said all we need to say, so until next time, that'll do. As always, thanks very much for watching, and until then, bye-bye for now.
Now, if there's anything else you need, hey, I got a pretty big plunger, and I'm pretty handy, so you just give me a call and...
Just go.